Um, Hi everyone. I'm Erik Jenelius, and I am very excited to be here today and give a talk in this seminar series, the Unite Sustainable Mobility Forum. And I will talk about how we can analyze people's travel patterns, how they move around in the transport system using automated data sources. But first of all, a few words about myself. I'm a professor in public transport systems at KTH Royal Institute of Technology in Stockholm. I'm also the head of the division of transport planning here at KTH. So I have colleagues working with logistics and rail traffic, car traffic, micromobility, etc. Myself, mainly involved in public transport planning and modeling, but also in urban mobility and micromobility, interested in transport system resilience and emerging technologies and data collection methods. So some of those things I will touch upon in today's talk. I also want to acknowledge my colleagues and co-authors in this work. I've collected some findings from several different studies. So we have Anastasios Skoufas, Francesco Ferranti, Matej Sebetzauer, Joanne Lin, Mohammad Magroor Zefre, Oded Katz, and Erik Almlöv, who are among the other authors and people behind this work. So first of all, what do I mean by travel patterns? Well, I'm using the term a bit loosely perhaps, but it can be down to individual people's travel behavior, looking at how specific people move about in the system. But it can also be more at the aggregated level, understanding flows of travelers and traffic going through the system. And I think it's also interesting to look at properties that start to emerge when you have a lot of different individuals traveling. For example, crowding, which happens when a lot of people want to travel at the same place at the same time, and there is not enough capacity for everyone to allow everyone to travel with no space restrictions. So I will come back to crowding analysis later in this talk as well. And when we analyze travel patterns, we can put on different lenses so we can apply that analysis to different types of studies. For example, we can look into the equity among different travelers or groups of travelers. I will show a few examples of that today as well. We can look at the efficiency of the system, the ability to move people in efficient ways, and of course various aspects related to the sustainability of the system. I will not talk so much here about the link between understanding people's travel patterns and the sustainable mobility, but I trust you can see those links. If we want to design a transport system that is sustainable, we need to understand how people move, if they already move in sustainable ways or not, and if not, how we can make the system align the system so that people can travel in more sustainable ways. We can analyze travel patterns to investigate the impacts of different policies or investments that we apply. So we can do before and after studies and see how travel patterns change and how people respond to policies, etc. We can also look into disruptions, unplanned things that happen. I will talk a bit about the pandemic as an example of a disruption and how people were affected by that. And we can use information about travel patterns as inputs for further modeling work, and also when we want to do forecasting, for example, we want to say something about the system, not how it works today, but somewhere in the future. The travel patterns alone will not tell us that, but we can complement the empirical results with some kind of modeling framework to try to make forecasts. So today I will focus mainly on public transport systems, but I also want to emphasize that much of what I talk about could also be applied to other forms of mobility. It could be shared mobility services, ride hailing, it could be micro-mobility services like electric scooters or shared e-bikes, etc. A lot of the data sources and data collection methods, as well as the type of analysis we could do, are quite similar between the different modes. So the talk I have divided into two main sections. I will actually spend some time on looking a bit specifically at the data and how we can collect data about that can be used to understand travel patterns and how we process that data to get something useful out of it. I hope that you will find this useful moving on in your studies and careers and so on. I think it's a good set of knowledge to have. And then I will give a few examples of analysis that we have carried out, which all of them build on this basic data collection and processing steps that I'll go through in the first part. So without further ado, why is data collected? And now we're talking about data we are not really collecting ourselves as researchers or as scholars, but we are using data collected by, let's say, a public transport authority or an operator. And they collect data typically to be able to provide an effective and reliable system services, to plan the systems when they design a network and set service frequencies, to evaluate the existing system, the level of performance they need to collect data. When ticket revenues are to be distributed among the authority and agent operators, you need to also have data to know how big the ridership was on different lines, etc. Some data are static, giving information about the network, where the stops are, and so on, where the population is located, and the demographics of the population, where there are certain points of interests, and so on. But other data is more dynamic, like the travel demand that changes over time, vehicle locations, where vehicles are at a given time, number of passengers on board and crowding levels, as well as incidents and real-time traffic information. So you can, of course, collect data manually yourself. But there are pros and cons of doing a manual data collection versus having these automated systems collect the data for you. The downsides of automated systems, I would say, are mainly the high investment costs. You will have to spend a lot of resources to install your system, and you don't have much control of the type of data that the systems collect. If you are a researcher, for example, then you have more control if you do the manual data collection yourself. On the other hand, when the system is in place, the marginal cost of collecting more data is usually very low with an automated system. So you can collect much larger samples of data. It's usually at a much more disaggregated level than manually collect data. You have less problems with measurement errors, or if you have them, you might be able to correct for them, and you can achieve more extensive coverage and in many cases almost real-time availability of the data. In the public transport system, we have a couple of main sources or types of data that are automatically collected. We have automatic vehicle location data, or AVL. This is information about where each vehicle is at a certain point in time, and that can be collected by different ways, GPS or other technologies. We have automatic passenger counts, which tells us how many passengers are on board a certain vehicle at a certain time, or how many board at each stop or alight at each stop. That can also be collected in different ways. By you can weigh the vehicle and see if it gets heavier, there are more passengers on board. You can put sensors in the doors that counts how many people pass on or off the vehicle. You can have counters in the ticket gates, barriers, or there are a lot of different ways of collecting that. And then not least, we have the automatic fare collection data, which I will talk quite a lot about today, which are the data that we can collect from the ticket system. Whenever passengers validate or buy a ticket, then we can use those records to understand where different passengers are at different points in time, and create their traces of how they move around in the system. And this system vary a lot in different cities and around the world. It can be on smart cards or mobile apps or credit cards and so on. But they're often collected in some form of database. And there are a lot of other types of automated collected data as well. I will not go into much about that. But in general, we are really in an era of mass data. There is a lot of data that can be taken advantage of as long as we are able to get access to that usually through some collaboration with the public transport authorities. These automated fare collection data, which I will focus on in this talk. The quality of that data varies a lot between different cities and different public transport systems, and it depends on how the ticket system is designed in each city. In some cities, you validate your ticket both when you enter a station or a vehicle and when you exit a station or a vehicle. So that gives us information both where the trip starts and where the trip ends. So that's great from an analysis point of view. In some systems, we also know exactly which route the traveler took between the start and the end point of the trip. If we know exactly which vehicle the traveler boarded, for example. In some systems, we don't know that. We only know where the trip started and in some cases where it ended. In Stockholm, we only have tap-in data, so we don't know where the travelers ended their trips. So that's something we need to infer from the data, and I will go through the procedure of how we do that for Stockholm. So I will focus in a little bit on the Stockholm case, which is where I'm located and where we have worked the most. Here we have AFC data. We have also AVL data and APC data from all the different modes of public transport. And it becomes quite a big sets of data when we collect them over time. So it's a couple of gigabytes of data each year. Nothing that cannot be handled by modern servers. So how does the data look? Well, it could look like something like this. These are examples of vehicle location and passenger count data from a bus line in Stockholm. In this case, it's bus line number 1. And each row here is a data record. It shows when the bus departed from a specific bus stop along that line. So that tells us something about the location of that specific bus at a specific time. And we can also, for example, see if that bus was delayed or on time by comparing to the timetable. We also have information about passenger counts in this data. So at each stop, we can see how many passengers boarded the bus, alighted the bus, and remained on board the bus. There are also some quite high resolution vehicle position data. This is data that is updated every 2 to 5 seconds. We get a new location of a specific bus. Well, that can be useful if we want to analyze if there are any delays occurring for the buses and where along the line those delays occur, for example. So the automatic fare collection system in Stockholm, every day we get about 2 million ticket tap-ins from this system. And it covers the commuter rail. We have a metro system. We have some light rail and trams. We have a lot of buses and actually a few ferry lines as well. As I said, it's a tap-in only system. In the metro and the train systems, you tap in when you enter a station. In the bus systems, you tap in when you board the vehicle. In the tram and light rail transit systems, it used to be some onboard crew that checked your ticket, but now it's mostly ungated stations. So there we don't get so much information from this data source. The AFC data could look like something like this. Again, we have a lot of records. Each record here is a specific ticket being used at some location in the system at some point in time. So we can, for example, see that in this case it was on a metro station. We don't know the vehicle here because we don't know. We only know that the ticket was validated at the gates of the station. But we know, for example, the type of ticket that was used. So in this case, this was a 90-day ticket. So let's go through the process, what we can use these tap-in data for, and how we can connect them into a sequence of trips. So let's say we have something like this. We have a tap-in on a bus at 8:49 in the morning. Then the same card is used in the metro at 11:06, and then in the rail system at 11:17, and then later again on a bus at 15:34. Well, how can we connect these points to one sequence? Well, we start by looking in an area around the metro stop here. Are there some? We look at the bus stops here. We try to find the bus stop that matches the bus that was boarded at 8:49, and then we pick the closest bus stop for that line to the metro stop that was used at 11:06. Since this was a bus line, we usually know exactly which vehicle that was used from the AVL data. And then we know when that bus arrived at this stop closest to the metro station, so we can compute the travel time of the bus trip for this passenger. So we know that this bus trip ended at 8:55. And now there was a time gap of more than 2 hours between the bus trip started and the metro trip started. So there was a long time in between those trips. So we think that this traveler did something else here in between. So we split these 2 trips into 2 different journeys. So a new journey begins now with the metro. We repeat the same procedure. Now in the metro system, we don't know exactly which train the passenger boarded, but we can at least look at which metro lines that pass by close to this rail station, and find the most likely metro train that was used by this passenger. And we do a similar thing again for the rail trip. We find the rail line that goes close to the next start of the next bus trip. Here there is also a big time gap between the 2 tap-ins. So we split these 2 into 2 different journeys. And basically, we repeat this procedure over and over, always looking at where and when the next tap-in from the same ticket occurs. So in that way, we create a sequence of journeys in the public transport system. We are fairly successful with this method. We can infer tap-out location and a travel time for most of the trips. in some cases, we are not able to do that. For example, if there's too big time going on between two tap-ins from the same ticket. But once we have gone through all that processing, we can actually start taking a look at the data. And then I think, start to see the big potential of the automatic fare collection data. This illustration is a heat map that shows the origins to the left and the destinations of every public transport trip over one day. And yeah, you can quite clearly see both the spatial distribution of the trips and also the temporal distribution. So not much happening throughout the night, but then the morning peak happens with a lot of travel. Then it is a bit more quiet during the day, and then the afternoon peak starts, and there's a lot of people traveling home from school and work. And then again, it goes more quiet in the late evening. So, and when we have the start location and the end location of each journey and the time between start and end, we can really use this information to build a lot of other things on top of that. For example, we can create origin destination matrices, which is very useful for a lot of different things. When we want to make forecasts about future travel demand, for example, we often express that in terms of the number of trips starting from one area in the city and going to another area in the city. And this data allows us to calculate these origin destination matrices as a very fine both geographical and temporal level. So we can, if we want to, we can compute separate OD matrices for weekdays and weekends, and we can split it into the morning hours, midday hours, and evening hours, and so on. We can also study how people transfer from one mode of public transport to another. For example, between metro and buses, or the other way around, and from one metro line to another metro line. All this kind of information is quite easy to obtain from automatic fare collection data. But there's one thing that is missing from this data, and that is that we don't know anything about who the traveler is. It's only an anonymous card ID number. So if you want to analyze something about the demographics of the travelers, we need to complement the fare collection data with other data sources. And we can combine the public transport data with statistical data at the zone level by trying to infer the home location of each card or each traveler. And we can do that by looking at where is each card most often used for the first trip of the day. And if we look at that over a period of time, then we can say that, okay, this traveler probably lives somewhere in this area. And then we can combine this information with statistical data at the zone level regarding income, education, household size, car ownership, and other interesting variables. And then we can do various types of analysis on top of that. So I will show a couple of examples of that. So this map shows where we have how we have inferred the home zone of different public transport travelers in Stockholm. All right, so that was the first part about the data collection and processing. So I will continue by giving a few examples of analysis of travel patterns that we have done on top of this data. The first example is trying to understand a little bit if there are different categories of users, of travelers. And so we take these travel diaries from the fare collection data and we cluster the users based on their travel profiles. For example, we can look at how they travel within a day, and we can find that there are some travelers that travel both in the morning and afternoon. These are the typical commuters, but there are some users that only travel in the morning and also some that only travel in the afternoon and evening. And these travelers probably have different expectations and needs out of the public transport system, that is good to consider. We can also cluster people depending on their weekly travel profiles. The biggest category of travelers are those that travel basically Monday to Friday, but not much in the weekend. These are the traditional commuters. But there is another group of people that travel frequently every day of the week. And then a few smaller categories that travel certain days of the week, but not others. And even some that only travel on weekends. So again, these different groups of people probably have quite different needs from the public transport system. You can cluster users based on how far they travel or how many different destinations they travel. And it turns out that some are very regular and only visit very few locations. Again, this is a typical commuting behavior that you go back and forth to the same place. But there are others who are more kind of explorers that they visit a lot of different locations in the system. I will move on to a specific analysis we have done related to the COVID-19 pandemic. So we used data, looked at data before the pandemic and during pandemic and after pandemic to see what happened to the travelers and how different user groups were affected. So I think similar to many other cities around the world, Stockholm was a lot affected by the pandemic. So the public transport ridership dropped significantly in the March, April 2020, and then has gradually recovered after the pandemic, but still has not fully recovered to the pre-COVID ridership levels. But during COVID, ridership went down, but who was it that stopped traveling the most and who continued to travel? This is something that we looked into using the fare collection data and this demographic information at the zone level that I mentioned. So we looked at how people change their travel frequency depending on where they live. And we clustered the zones in the Stockholm area based on their demographical attributes. And we ended up with 5 different clusters, which are quite distinct from each other. The first are the areas with the lowest income and education levels, high levels of unemployment, many foreign-born citizens. The second cluster, they have slightly higher income and slightly lower unemployment. The third cluster are more single-family houses and more rural areas. The fourth cluster are high income and high education people, young people. These are areas, the urban central areas typically. And the fifth cluster are also high income education, but these are more like villa suburbs, single family houses, etc. And when we look at how people belonging to the different clusters here change their travel frequency during the pandemic, we see some clear differences that people in the first 2 clusters, they continued to travel to the largest extent. These are the ones with the lower income, lower education levels. But people from the clusters 4 and 5 with a higher income and education levels, they stopped traveling to a larger extent. So we saw some clear distributional equity effects during the pandemic. Moving on to another aspect which is related to pandemic, which is looking at the crowding and crowding exposure. So how much crowding are you exposed to when you travel, when you use the public transport system? We know that people dislike crowding in general, but especially during the pandemic, of course, crowding became something very negative. It could actually be mean you have a higher risk of transmitting the virus. But more generally, we dislike crowding because of comfort, safety, and other reasons. So we want to analyze crowding exposure, and we measure that by looking out of your total travel time. How much of that time do you spend traveling in crowded conditions? And what is crowded conditions? Well, that could be that you have no seat available, or it could be that you have to sit next to someone else, so more than half of the seats are taken. And we can use the automated fare collection data to compute the crowding inside the vehicles as well. Since we know exactly when and where each traveler were at a specific time, we can aggregate all the numbers, so we know how many people were inside a specific vehicle at a specific time, and in that way we can compute the crowding throughout the system. So we analyze crowding exposure in the same way, in the same periods, pre-COVID, during COVID, and post-COVID. And we find that crowding was worse before the pandemic, and then we did not have much severe crowding during the pandemic, and then it has returned to some extent after COVID, but not to the same levels as before. But again, coming back to these social clusters, who experiences the most crowding? Well, during COVID, it was cluster one, this traveler from the lowest socioeconomic cluster that were most exposed to crowding, because these were the travelers who continued to travel the most. But now after COVID, things have shifted a little bit. So it's actually now travelers in this cluster 5, the suburban high income, high education group that are most exposed to crowding. Because they tend to use the system in the where we have most crowding taking place. Moving on to analyzing crowding, we can explore whether people take crowding into account when they choose how to travel, which routes to travel through the public transport system. So we can use the data to analyze if people use different routes and why they seem to use different routes. Does crowding play a role? I will not go into, I will not talk about the modeling aspects here, but essentially we can estimate the impact of that crowding has on the route choices of people. And we do find that crowding has a negative impact for people. So people tend to avoid routes with more crowding and prefer to choose routes with less crowding. Is again something that can be useful for public transport planners when they develop and plan the system. The final example I want to go through is to look at a particular group of travelers and understand that specific group, the travel patterns of that group. And here I'm taking school students as an example. You could, of course, analyze other traveler groups as well. But school students are interesting for a couple of reasons. They are a quite big group of travelers overall, especially in the morning and early afternoon peaks. Quite a big part of the travelers are actually students going to and from school. It's also pretty simple for us to identify the school students in the data because they have a special ticket product. So we can quite easily filter out school students from the rest of the travelers. So again, we have explored the socio-geographical differences among school students belonging to these different social clusters. So we wanted to see if students from different clusters use public transport to travel to and from school in different ways. And it seems that there are some variations between them. For example, the students living in more rural areas seem to use public transport less, but the students living in the more urban areas use public transport more. Also, we can look into the daily activity chains of the school students. We identify not only their home location, but also where their school is. And then we can guess which trips are trips to school and which trips are from school back to home, or which trips are from the school to other types of activities. And then we can explore if students from different social clusters travel in different ways, if Some groups of students have more after school activities where they go by public transport, for example. And if the travel times differ between different groups of students. And here we can see that students in the rural areas of the region tend to have longer travel times on average than other students, for example. So I reached the end of my talk today. I basically went through the process of collecting some different types of automatic data that can be useful for understanding and analyzing the public transport, and how we can process that data into something useful, and then giving a couple of examples of how it can be used. But there are for sure tons of other use cases where this type of data can also be used. All right, thank you very much.